Have you ever stopped to think about what gives a machine its precision? You know, how a robot arm can perform delicate surgery, or how an electric car delivers power so incredibly smoothly? Well, the answer to all of that lies in this one brilliant concept: control.
So, take these three things: a drone flying through the air, a robot on a factory floor, and an EV on the highway. I mean, they seem totally different, right? But they all share a fundamental secret.
And that's it, right there. At their very core, all of these amazing technologies are about one thing: telling a motor exactly what to do and when to do it, perfectly. Without that precise control, they're literally just hunks of metal.
So, to really get the magic of control, first we've got to see what happens without it. So let's meet both the hero and, well, the problem of our story.
Okay, so this is a DC motor. This little guy is the workhorse behind so much of our modern world. But here's the thing: you can't just tell it what to do and hope for the best. To really control it, engineers have to build a mathematical model first. Think of it like a digital blueprint that perfectly describes the motor's personality. You have to know how it's going to react before you can teach it anything new.
All right, so we've got our model. We understand how this motor should work, at least on paper. Now it's time for the moment of truth. Let's see what this thing actually does when we just give it a jolt of power.
The experiment is super simple. We have a target speed, we'll just call it a value of 1. We're going to apply power and see if the motor can get there all by itself. So what do you think's going to happen? And oof, there it is. Just look at that red line. It starts to climb, sure, but then it just peters out. It flatlines way, way below our target. It doesn't even get close. This is what's called an open-loop system. It's basically flying blind. It has no feedback, no guidance, and zero idea if it's doing a good job or not. And yeah, this level of performance is just not going to cut it. I mean, imagine your car's cruise control being this lazy, or a surgical robot being this sloppy. No way. Let's really break down just how bad this is. Let's put some hard numbers to this failure. It takes almost 3 seconds just to get to its final sluggish speed. But the real killer, the stat that tells the whole story, is that first one, a 90% accuracy error. It only achieved 10% of the speed we actually asked it for. That's a massive, massive failure. But okay, don't worry. This is where the story gets really good. Our slow, inaccurate little motor is about to get a serious upgrade. It's about to get a brain. Meet the PID controller. Now, this isn't a physical part we add on. It's an algorithm, a set of rules living inside a computer. Its job is to constantly measure the motor speed, compare that speed to our target, and then make tiny, continuous adjustments to the power. It's a non-stop, intelligent feedback loop.
So how does this brain think? Well, it's got 3 parts. First is P for proportional. That's its immediate reaction. If you're far from the target, it pushes hard, like stomping on the gas. Then there's I for integral. This one looks at the past. It notices if you've been consistently too slow, like going up a hill, and it adds a bit more steady power to compensate. And finally, the really clever part, D for derivative. This one looks to the future. It sees the target coming up and starts to ease off the gas so you don't fly right past it.
Okay, so we've seen the problem. We've met the solution. Now it's time for the payoff. Let's put them side by side and see the difference a brain really makes. And wow, just look at that. The difference is literally night and day. That sad red line way down at the bottom, that's our original uncontrolled motor. But that purple line rocketing right to the target and locking on, that's our motor with its new PID brain. It's fast, it's precise, and it's stable.
So just to remind you, this is where we started. A 90% error. A system that was almost completely wrong.
And this is where we are now. 0. Absolutely 0% error. That controller didn't just reduce the error, it completely eliminated it.
So here's the final scorecard. The PID controller is 3 times faster, settling in at under a second. Now you do see that tiny bit of overshoot, about 8%, and that's often the price you pay for being so quick. But it's tiny and it settles down fast. And of course, the steady state error is 0. This is a total victory across the board, a complete game changer.
So, okay, this is really cool. We've fixed one motor, but the real takeaway here, the big idea, is so much bigger than that.
This is all about a fundamental law of engineering: feedback control. The idea is simple. You measure where you are, you compare it to where you want to be, and then you make a correction. That simple loop, measure, compare, correct, is one of the most powerful ideas in all of technology.
And I mean, it is everywhere. You use feedback control systems every single day. The cruise control in your car, that's a PID controller. The thermostat in your house, same thing. An airplane's autopilot, the autofocus on your phone's camera, All of it works on this exact same principle of measure, compare, and correct.
You know, the university paper we used for this explainer sums it up perfectly. By adding a simple but intelligent controller, you can transform a dumb, imprecise component into a reliable, high-performance system. You give the machine a brain, and it changes everything.
It really makes you think, doesn't it? Now that you know this secret, this loop of measure, compare, and correct, you start to see it everywhere. So my question for you is, what other uncontrolled systems out there, maybe even in our own lives, could use a little bit of feedback? Something to think about.